MicroSD cards are the most compact and dense commercial data storage format there is. For example, if you took a shoebox and filled it with microSD cards, you could store every single movie and TV show from your favorite streaming platform, and it would only take up a small fraction of the shoebox. In fact, if you could get your hands on hundreds of millions of microSD cards, you could store all the data of the entirety of the internet inside your living room, and you would still have a little space left. So let's answer the key question. How exactly are microSD cards able to store so much data in such a tiny space? Let's open one up and find out. Inside, we find a multi-layered sandwich of integrated circuits, resistors, capacitors, hair-thin wires, and other metal layers, all squeezed together in a marvel of miniaturization, packaging, and sandwich making. Most of these integrated circuits, called dies, are NAND flash chips, and they're the structures that actually hold the data. These NAND flash dies are organized into 2 stacks of 8. However, because they're stacked one on top of the other, each die must be incredibly thin, equivalent to the thickness of a single strand of hair. Despite being so thin, there's a ton of incredible engineering packed inside. Let's zoom in even further to a nanoscopic view of one of these NAND flash chips. Here we have a massive 3-dimensional array of NAND cells, also known as charged trap flash. This array stands over 200 layers tall, and across a single die there are roughly 72,000 cells wide by 48,000 cells deep. When we zoom all the way in, we can see the individual charge trap flash storage cells, each of which is only about 100 nanometers across and holds 3 bits of data by trapping electrons inside a thin layer of silicon nitride. This 3-dimensional design, with hundreds of memory cells stacked one on top of the other, is the key to achieving such incredible memory densities. But how is it built? Well, like all microchips, it's built on a silicon wafer inside a semiconductor fab. There are thousands of steps, but the basic idea is this. First, layer after layer of alternating silicon oxide and silicon nitride is deposited to build up the stack of 100 or so storage cells. Next, the massive grid of 72 by 48,000 cylindrical holes is etched straight down through all the layers, creating channels which are subsequently filled with a complex sequence of materials. As a result, a single memory cell is formed at each intersection where a vertical column crosses a horizontal layer of silicon nitride. This forms the first deck of 100 memory cells. The entire process is repeated with another series of layering and etching vertical holes to build the second deck of 100 or more memory cells, which must perfectly align with the prior one. Next, wires are added across the tops of the columns and connected to the read, write, and erase control wires that select each layer and step down the sides of the array, like a staircase. A protective insulating layer is then added on top, encapsulating the delicate wires on the die's top surface. With the top side complete, attention turns to the bottom. The silicon wafer these chips are made on is far too thick on its own, so the underside is ground away until each die is only about 40 micrometers thick, which is, as we said earlier, the thickness of a single strand of hair. From here, each die is thoroughly tested, and the flawless ones are cut out from the wafer and stacked 8 high, with each die offset slightly from the one below it. This offset leaves a row of bond pads exposed along the edge of every die. Incredibly thin bond wires are then welded onto these pads, connecting each die down to the layers of interconnects beneath the stack. The interconnects route over to the controller die, which in turn connects to the contact pins on the outside of the card, allowing data to flow to and from the stacks of NAND flash dies. Finally, the entire package is sealed in epoxy and then encapsulated in a thin plastic shell. And that's the whole marvel. Over 200 layers of charge trap cells, etched, stacked, and wired with nanometer precision, all sealed into something smaller than your fingernail. It's semiconductor engineering at the absolute edge of what's physically possible. And if you want to follow where that edge goes next, that's what today's sponsor delivers. This video is sponsored by IEEE Spectrum, the world's leading engineering magazine, with over 60 years of independent, unbiased journalism. Stacking silicon is the future of semiconductors, and Spectrum is all over it. In the April issue, they break down high-bandwidth memory, stacks of ultra-thin DRAM dies that feed AI chips the terabytes of data they need every second. And then Dulay recounts how a lab accident transformed an ordinary transistor into an artificial neuron that could dramatically cut AI's power bill. The best way to read Spectrum is through the print magazine, a curated, distraction-free deep dive at your door every month, with no ads, no pop-ups, and no algorithm. If you made it this far into a video about charge-trap flash, it's basically made for you. Get 20% off an annual subscription using the QR code on the screen or the link spectrum.ieee.org/brancheducation down in the description below.